Good morning, everybody. Well, we have to accept that some people will be still coming because the coffee break is, as I'm saying, one of the most important parts of the conference. Not only enjoying the coffee, but networking. Anyway, I got great honor, and I am very happy to introduce the next plenary speaker, which is Professor Sharifah. And a short introduction. Her education started at UMIST, which we've got in common, and I'm very happy because we are both alumni. She continued with PhD at UTM, and currently she is director of so-called Prospect Process System Engineering Center at the University of Technology Malaysia, which is one of top universities in Malaysia and very high in the ranking over the world. And I've got something common with this university because I am a receiver of honorary engineering degree, so I'm more or less from the family. She developed what is very important to commercialize a water minimization software called Optimum Water in the spin-off company, Optimum System Engineering. She is consultant for many companies with very nicely sounding names like Shell, CCM Chemicals, Oleon, and some others. She's a proven expert in process integration, and she's co-author of a highly successful book published by the Reuters in Berlin, Process Integration and Intensification Saving Energy and Resources, which recently received the second edition. You know, it's quite easy to get, if you've got some experience, one book, but to get second edition, it means that the first edition was sold out. And this is a big recommendation. And she also received a number of national and international awards of IChemE, Institute for Chemical Engineering of UK, as highly commended Sir Frederick Warner Prize in Germany, Green Talents by Thomson Reuters, Malaysia Rising Star, ASEAN Levels, and many others, but you know, it's not my lecture, it's her lecture. So Professor Sharifah, please take your time. Thank you.
Okay, thank you very much to the chairman, Prof. Yiri Klemesh, for the kind introduction. Good morning, ladies and gentlemen. Thank you for coming to the talk after the nice tea break. So the title of my presentation will revolve around water minimization. So water is very important in our lives. We drink water, we use water for washing our clothes, we use water for energy generation, and so many things. And if you look outside the La Torre Hotel, you have the beautiful blue sea, and water is just everywhere and very, very important. So if you look here, this one is a very beautiful river, a blue river. But unfortunately, in many places, the water is getting more and more polluted. And what could be the reasons of this pollution? Sometimes industries, if they are not concerned with wastewater, some of them do not properly treat their wastewater and they discharge it still polluted. And there are also agriculture, domestics, and many, many other sources which pollute the water that we have. Even in Malaysia, some statistics that we have found, we found that almost 40% of the river in Malaysia is being polluted already. And another important thing is the growing population. So if you look at the growing population, 1,800, the population is only 1 billion people. But in 100 years, in 1900, the number of people in the world grows to 2 billion. And now, which is 2018. So I took the worldometers, which record how much is the number of the current population of the world. The number of population in the world currently is at 7.6 billion people. So imagine from just 90 years, we have grown from 2 billion, within 90 years only, not 1,000 years. We have grown from 2 billion people to 7.6 billion people. So that is like 4 times the growth in just 90 years, right? So what does more population means? It means also we need more water, more clean water for all of the people. And water is very important in our daily lives. And you can see that various products consume various amount of water for the production, for the plantation, for the and many things. So like, for example, the bread that we eat this morning, maybe you have your breakfast in the hotel, it consumes about 1,608 liters of water per kilogram of bread. And imagine how many of us in this conference, about 400 of us. So let's say 400 of us eat how many 1 kilogram of bread for this 4 days conference. So we already multiplied by 400. So much water has already been consumed by all of us. And we haven't talked about the 7.6 billion people yet. And you can see all the various products consume water. Even our coffee, our milk, our cheese, our chocolates, everything that we use, all the products that we need, all needs water during the production and so on. And this is very important. And we should do something to address this, because according to the statistics as well, 2.4 billion people will have no access to clean water currently already. Okay, another important issues. Everyone have been talking about energy, climate change these 2-3 days. And climate change does not only affect energy, does not only raise the temperature of the world, it also induces a lot of issues that affect water. So you can see that if, for example, the temperature goes high, it becomes a drought season, a very hot season, the water might dries up. Yeah? And if the surface water dries up, it also means we have more or less access to water for our daily lives. So climate change is a big issue. I can live without my smartphone. Yeah, I can live without energy, not to charge my smartphone, no lights. Maybe I can still live, even though I'll be bored because I can't contact everyone. But we cannot live without water. Yeah, we need water for our everyday lives. And water is also very connected to many things. It's connected to energy, it's connected to food. You need energy to pump the water, to distribute the water, to clean the water treatment and so on. At the same time, you need water to generate steam. And then from that steam, you can use it to move your turbine and generate energy. And water is also very important for all the food products, as I mentioned, for agriculture, plantations, and so on. And at the same time, food, like biomass and so on, it contributes to energy, and also the agriculture and so on also goes back to the water supply chain. So by taking care of water is also very important, because we'll also be taking care of the whole food, water, and energy nexus that many people are talking about. So that's about the importance of water, maybe something you have heard in so many lectures. So let's look into the water cycle. Yeah? So how do we get clean water in the first place? So normally we have a water supply, a source of water. It could be river, it could be lake. So it's a source of water supply. And normally to have clean water, it needs to go to a water treatment plant. And then after that, the water being clean, it will be distributed to the consumers. And the water is being utilized by domestics, agriculture, industries, and so on. And after water is being used, we will generate wastewater from the usage. And this wastewater, we need to collect it, send it to the wastewater treatment plant before finally being discharged back to the water sources. So these are the common water cycle to get clean water and how it goes back to the water source. So we mentioned just now that there are 7.6 billion people now. And we mentioned also water is getting more polluted and so on. So what could be the solution to solve water issues or water scarcity of the world? Could it be that we need more water? Could it be that it means we need to find more alternative water supply? So if we look at water supply, it could be river and stormwater, as I mentioned just now. But the issue now is the pollution, emerging pollutions and many other things going into the water, which makes it harder to treat and maybe more expensive to treat, especially the emergent pollutant. Like sometimes we throw antibiotics and other things into the water. So this is very hard to be treated. We have superbacteria and so on. So many things we have to consider when water is being polluted. And people also look at other alternative water sources like groundwater. So groundwater is a good alternative, but if you over-extract groundwater from the ground, then it will incur more long-term problems in the future because water is actually being replenished inside the ground. So when you extract it too much, it doesn't go back to the river. You will have lots of long-term problems with plantations, and then you will have holes going to the roads and so on. Yeah. So people have also been talking about desalination, another famous technology which people go into. So desalination is great. You can use seawater, which is very, very abundant. We have seawater almost everywhere. But the problem with desalination is energy. It's very energy intensive. It requires about 8 to 10 times more energy intensive compared to treating the surface water. And another thing that people have been talking as alternative water is wastewater reclamation. So maybe you have seen the advertisement where water is being flushed from the toilet, flushed down, and then you go to the treatment, and then suddenly it goes to your water tap, and then someone is drinking. So this is wastewater reclamation. And it's good, but the problem is public acceptance. Not many people, after they see water is being flushed down to the toilet, have the gut to drink wastewater reclamation. So although it's cheaper compared to desalination, but the public acceptance may be lower for this wastewater reclamation. Okay, so we talk about water supply. We have growing population, all the products need water. And we have so many water supply technologies which I have mentioned, but water supply is only one part of the story. So the other part of the story that we have to look is at the demand side. So you can have all the alternative water supply, but in the first place, maybe you do not need to have that much of water supply in the first place. Maybe in the first place, you can try to reduce the required water consumption for all the products first, so that in that case, you don't need to build such a big desalination plant, you don't need to reclaim too much wastewater and so on. So water demand management is very important, and you have to consider it when you are doing a planning. So don't just plan building a bigger desalination plant and so on. Plan also what should you do in order for you to reduce the water demand side as well from the consumer perspective. So what can we do? We can leave it to the government. We can let the government build a desalination plant for us. We can let the government choose whatever technologies which is great for the country. But the problem is, let's say they do go for desalination plant, it also means that your water tariff will be higher. So now if your water is from surface water, maybe it's still very cheap, but when we are going towards desalination, it will mean we as the consumer have to pay higher water tariff. So more money going out from our pockets. In another sense, if we let the government take charge, of course, they want to reduce the wastewater pollution, the pollution to the rivers, seas, and so on. So we will have more stringent regulations. So the wastewater treatment plant, you have to build maybe bigger capacity, you have to treat it into more stringent standards, and so on. And it will incur more capital investment to the industries, and so on. And the problem, again, is climate change. Something that we have to plan from now as well. What happens if the surface water dries out, for example? So what should we do? So sometimes what are the alternatives that we can have to make sure that our water supply is reliable instead of unreliable because of climate change effects and so on. Okay, so let's talk about demand side. So let's say all of us can play a part, not just leave to the government to build the desalination plant or whatsoever. So what we as the consumer should be doing, so of course the easiest one is to change our behavior. So in the first place, we should try to save water. Yeah, maybe when we are brushing our teeth, we have to close the tap and so on. So try to reduce water as much as possible. Try to educate our children, our students. Most of us are lecturers or researchers here. Try to educate all the community on the importance of saving water. But, another difficult thing, we can try to preach people to save water, change behavior, and so on. But sometimes changing behavior is not so easy. It's easier to control a machine as compared to controlling someone and say, you must do this. I think if you have children, you do understand it's not easy to change the behavior of people. So we need to instead use technologies. We need to design our system because behavior is good to do, but we also need to think how to design our system in order to reduce to enhance the water demand reductions. Yeah? Okay, so how do we engineer sustainable water system? That is the next questions that we are going to address. Okay, I'll be talking from the industrial perspective because in my field of work, I work a lot on how to reduce water from the industries. But you can also implement this for other facilities like buildings and so on. Yeah? Okay. When we want to reduce water or we want to do anything at all, we should always look at the bigger picture. Yeah? So this one is like a blind man. So we have an elephant here. And if you let a blind man, for example, hold the tail of the elephant, he'll think that this elephant is actually a rope. And if you let him touch the body of the elephant, maybe he'll think it's a wall. And when you hold the feet, maybe you think it's a tree. So it's very, very important that when you want to reduce water, you should not look from one angle or one perspective only. We should always look from the bigger picture in order for us to find the actual problem or the situations of the thing. Yeah? So we have published some work in how to minimize water holistically in the Chemical Engineering Journal. And also have some books. If you're interested, you can read the books or the magazine. Okay, so what is the concept that I want to highlight here? So we have the water management hierarchy, which can be used to guide the water minimization. So what is a water minimization hierarchy? First of all, it has the water reuse. If we can reuse water, so let's say you use water from the kitchen. After the water comes on from the kitchen, maybe you use it to water your plant. So this is an example. So this kid, after washing the hand, so the water from washing your hand is actually not so dirty. So you can actually consider to use this water from washing hand to flush the toilet. Why do you need clean water up to tap level to flush a toilet? Do you really need it? No, right? You don't need clean water for everything. Some of the things you can use second-grade water or water maybe with a bit of contaminants, but it can still be used for the processes. So this is a very good example. The second thing that you want to consider to minimize water is source and demand manipulation. How can you eliminate or reduce water in the first place? Maybe, for example, this is a composting toilet. It does not require water at all. Toilet, maybe previously, if you use the old toilet, it used about 12 liters per flush. Now, with a dual toilet, maybe you use 4.5 liters per flush. But if you go into composting toilet, you eliminate water totally. So there is a way where you can manipulate or minimize water by changing your technologies. Maybe change to composting toilet, go for laminar flow water tap, and many, many other things. So these are source and demand manipulation. The next thing you can minimize water clean water requirement is by using outsourcing. What is outsourcing? So outsourcing is like rainwater harvesting. So we have lots of rain in Malaysia, not like in Europe. Malaysia, in the rain, maybe you think it's a storm because the rain is very heavy in Malaysia. So rain is a very good resource. If you can harvest it, it's not as clean as tap water. There are also some contaminants in rainwater, especially if you harvest it in the roof. So you will have to clean it up a bit before you can use it. But it is also an alternative water, and you can get it by harvesting it from your rooftops and so on. Yeah? And lastly, after you have considering reusing, playing around with elimination, reduction of water, and then looking into outsourcing, maybe you can also look at regeneration. So what is regeneration? Regeneration means, let's say I cannot directly use the water for my process. So maybe I need to partially treat the water before I can use it for a process. So that is regeneration. And if we want to minimize water, we have to consider all these 4 angles before we resort into using clean freshwater tap. Yeah? Okay, so next thing. Okay, so it sounds very familiar. It sounds like 3R concept: reuse, reduce, and so on. So this is so simple. I can just use common sense to solve all this problem. But the problem is when you have, for example, in the industries, you have so many water streams. Even in domestic, you use water for so many things. So you have so many processes which use water, and at the same time, you have so many wastewater coming out after the water is being used at the processes. So if you want to reuse water, sometimes you have to know the contaminant limit of that water. So if you want to reuse from ablution to washing car, you have to see if you can reuse it directly, or if this one, the contaminant is higher, maybe you have to mix it with other water sources which is cleaner, or maybe even mix it with fresh water before you can utilize it for a process. So there are actually some calculations you need to consider before you can do water reuse. You need to know which one is the best reuse match. You need to know what is the blending options possible, what should be the ratio of mixing, and how do you ensure that the contaminants, if you are using it, for example, to wash your clothes in a laundry, is not affecting the washing machine performance, for example. It doesn't make fouling, for example, and it doesn't affect your equipment. Or if it does affect your equipment, so what are the maintenance or the operability that you need to consider? Yeah? And if you talk about water management hierarchy, there are so many options. You can change the water tap to so many different technologies. If you have a toilet, you want to change your toilet to vacuum toilet, composting toilet. So there are so many options that you can do from all the water management hierarchy angle. So the next question is, which one of the strategies or the technologies that you should choose for your facility? And another important one is, of course, economy. You may want to reduce water up to zero or zero water, but it may not be economical because maybe the technology will be too expensive and you may not have the budget for it. Yeah? So we need to find a trade-off. It's good to save water, but at the same time also, what is the cost and which one should you prioritize? Like maybe you can go for no cost and low cost first before you go to the higher cost measures. So we need to find ways to minimize water holistically and systematically. And system approach is one of the best way to address this. You have so many constraints I have mentioned just now. So we need to look at it from systems approach. So system approach for water minimization, there are 2 typical approach. One is the insight-based pinch analysis method, which use graphical approach or numerical tools. Another one is the mathematical modeling tool. Both have their own pros and cons and their own strength. So pinch analysis, I have done quite a lot of research in this area. So one of the methods that our research center has introduced is what we call the cost-effective minimum water network technique. So it doesn't require any modeling. You can just solve this by using Excel. So it's also made from simple graphs, So when you plot it using the graph, if you are proposing to an industry, it's very easy to explain to the industrial people why the water reduced, why should you select this technology from that, how much is the blending options, and so on. So we can use the water pinch technique, which cumulative mass load versus flow rate, and from there you can plot all your water demands and water sources and determine your potential fresh water needed and wastewater target. And the good part about this graphical approach, you can also use it to guide the selection of water management hierarchy that I mentioned just now. So when you have options to eliminate, reduce, outsource, or regenerate, so let's say I eliminate something from the demand, what will happen to my freshwater target? When I harvest rainwater, for example, so I will have more water sources. So what happens is this source line will become longer. So will it reduce my fresh water, or maybe it will increase my wastewater instead when I harvest more rainwater? Yeah? And if I want to regenerate or pre-treat some of my water, for example here, my water source is too contaminated, but my demand requires cleaner water. So I may want to treat part of this wastewater source to a bit cleaner in order for me to be able to satisfy this demand, water demands, so that I can reduce my freshwater targets. So water pinch is a very powerful tool, especially the graphical pinch, because it can give you insight based on what happened when you do this and do that. But of course, the downside of pinch is it can only cater for single contaminant system, and the problem is when you have multiple contaminant system. But it can still be solved by using pinch if you take into consideration zones, and then you take, for example, the highest contaminants limit, and there are ways to do it actually. Yeah? Okay. So cost is also important. So our group have also introduced a method where you can screen the water management hierarchy by using a tool we call the systematic hierarchical approach for resilient process. So again, it's a simple graphical tool, investment versus annual savings. By using this tool, you can target, for example, let's say the first technology that you choose save a lot of water, but the cost is very high as well. The investment is very high. So you want to check what should be the next best technology. Maybe it won't save water as much as the first technology, but the cost might be cheaper. So by using this curve, you can have your payback period target. So let's say this payback period initially was 10 years, and your payback period, your target is 2 years. So you can plan, okay, I should not be using this technology because it's using too much investment with too little savings. So I should change it into maybe a lower investment technology, but maybe it gives less savings. But at the same time, I try to maximize everything in order to achieve the most and maximum saving with the limited investment limits that we have. So SHAPS is a very powerful tool if you don't want to go into mathematical modeling to do cost screening. So it's an interesting method, and if you're interested, you can read the method in this journal. Okay. Mathematical modeling. I believe most of you are experts in mathematical modeling. Maybe some of you are doing research in this. It's also a very powerful tool. You can put all the constraints in there. And we have also done some work in this area from the water management hierarchy. So you can also use mathematical model to solve this problem. Okay. So these are just some examples. We have implemented this water minimization for the demand side for several industries. Like even in UTM itself, we have implemented in the MOS. And we have managed to reduce about 95% of the fresh water by considering all the hierarchy that I mentioned just now, reuse, eliminate, reductions, and so on. We have also done some study for MIMOS, which is a semiconductor plant. Again, a lot of reductions if you consider all that. And the payback period is also very good. It's only about 4 months. Yeah? And other companies as well. So these are just some sample projects. Okay, next question that I want to throw. Water reuse that I mentioned just now, if we can do it for a single plant or maybe for your building, it will be great. Yeah? It will be very great if you can recycle or reuse water from one process to another process. And the good thing is, if you recycle something, for example, let's say this is La Torre Hotel. So I recycle the water from bedding. Let's say the water from the shower. We collect the water from showering, and then we use it to flush the toilet. So if we can utilize the water reuse within this hotel, it will be great, because it means the pipeline is only within this hotel. Yeah? And it will be more cheaper if you build it within this hotel for the pipeline, for the pumping, and so on. But the problem is, sometimes there is no economy of scale. And so sometimes some places, they have a lot of wastewater, but maybe the wastewater is not so clean. Maybe it's very highly contaminated. So they don't have, they do not have wastewater which they can reuse. And let's say they have some others, but maybe the flow rate is so small. So let's say there is another plant next door which have higher water quality, which they can, but they don't use it for their own. Maybe they can actually send it to the plant next door. So a reason that maybe water reuse is not possible for a single facility is probably because there's no economy of scale, no suitable water streams which is suitable to be reused. And another thing is maybe no expertise. Yeah? If you want to reuse water, you need to have some experts that can advise you, like what will happen, is the contaminant limit suitable, will it affect the process, what will be the cost involved, what will be the risks or the sensitivity that you need to analyze. So if you want, maybe if the La Torre Hotel, for example, they want to implement this water reuse, but they don't have the expertise because they're not the researchers, for example. So they might be scared to go into these water reuse schemes. Yeah? So the next question that I would like to pose is, let's say we have a lot of buildings or a lot of industries which is nearby to each other. And maybe what we can do is, instead every building have their own water reuse system, we can consider centralizing the water reuse system instead. So how do we do that? Maybe you have heard the industrial symbiosis. So industrial symbiosis concept says that you can exchange water or waste or whatsoever among other industries. So maybe you don't need that water source or waste, but you can actually sell it to another company which may want that waste or wastewater that you don't want in the first place. So this is the industrial symbiosis concept. But the question is how to make it a reality. We do want to exchange waste among industries, but how do we make it happen? That is the next main challenge that we need to address. There is a famous concept called Eco-Industrial Park, EIP. So according to the Eco-Industrial Park, the waste from one company becomes a resource for another company. In fact, UNIDO, they have a guideline or a booklet which tells how to do the Eco-Industrial Park planning. And worldwide, I have checked, there's about 250 industrial parks which have actually integrated their resources among each other. So if you want to reuse water across industries, it's possible, and it's part of the EIP concept. Yeah? Okay, how do we exchange water among industries? So let's say I have three industries. All of my plant consume fresh water in the first place, and it also produces wastewater. So I have this industry 1, industry 2, and industry 3, which is nearby. I want to exchange the water. I want to reuse the water. So maybe this water from plant A, I want to send it to plant B, or maybe I can send it to plant C. So is it the way that we should make all these small pipelines? For example, from this process, I send it to plant A, and then from plant A, I send it to plant C. So this is like not very practical, because it means you have small pipelines with small flow rate. And imagine if you have small pipeline with small flow rate, you need to pump it from this hotel to the next hotel. So it's not going to be very practical. So you don't want to do small pipelines. You don't want to connect one process from one industry to the other industries, because this will mean more pipelines, more pumping, and it's not practical and maybe not feasible because the flow rate is too small and the capital cost will be high. Yeah? So one is the problem. You don't want to do water integration among industries by using small pipeline because it will be too complex, too many pipelines. And there will be a lot of long pipelines that you have to consider for all the small pipelines. And another important issue is who's going to pay for building all the pipelines and all the pumping. So let's say these three plants, they decided to work together and exchange their water reuse. So who's going to invest building pipeline from plant A to plant C, or plant C to plant B, and plant C to plant A back, for example? So the issues will be who will be investing in building this pipeline. And let's say they need to have a pump, so there will be an operating cost to power that pump to pump it. So who's going to pay the operating cost of this pump? And let's say something happens, who is going to do the maintenance of the system? So when you are doing industrial symbiosis, it's not maybe it's possible if you come from one mother company, but let's say this company is not interrelated with each other. It's very hard for them to discuss, okay, I have some water which can be reused by you, so let's exchange water. It's going to be hard for them to come to terms on who will pay, how much can be transferred. And another important thing is, will they want to share their information? So for example, let's say plant A. So someone from, let's say the initiator is plant B. So someone from plant B says, I want to do water reuse for the 3 plants. But plant A will say, hey, why should I give my data to you? Because our data is confidential. And plant C also do not want to give data on their water streams to plant B. So in the end, plant B, even though they have the expertise and they want to help to exchange water among the 3 plants, but maybe because of confidentiality, the plant will not want to share data with each other. So this is among the issues when you want to make centralized water reuse a reality. Yeah? And another thing is, for the industries, normally they are more interested on their production. So do they have time, for example, or do they even care to exchange water among industry? So this means that if you want to make water reuse exchange, normally it will not work by 3 industries talking to each other unless they have a very strong drive, maybe regulations or whatsoever. So another possible model, which I want to discuss here, is it possible for us to propose a middleman instead, who can help to collect the data, who have the expertise, who will meet all the plants and do the negotiations. So in that sense, if someone needs to sign the non-disclosure agreement, it means only one person will sign the non-disclosure agreement with the companies. And all the other companies, they will not know the other people's data. So only the middleman that collects the data, keep the confidentiality, and so on. Yeah? Okay, so maybe you are familiar with feed-in tariff or net energy metering for renewable energy. So what we are proposing here is something for water instead. So normally, if for renewable energy, it's quite common that you have surplus of electricity. Maybe you have a solar PV at your house, so you want to sell it to the grid. And then, for example, when you have deficit of energy, you can buy from the grid. So imagine now, we can do it also for water reuse system. So let's say we have a set of industries, and all these industries, they have wastewater with different quality. So let's say I have quite a good quality wastewater. Maybe the purity is still very high, and it can actually be reused. What we can do is, maybe we can have a water meter for the water reuse and sell it to a centralized water reuse header. So this centralized water reuse header will be managed by a middleman. So what happens is, the middleman, they will go to the industries, and then maybe they can do some audit. So which wastewater stream, which has high water quality, that they can tag into this centralized water reuse header. And they can also maybe have several headers. Maybe one is within this range of contaminants, the other one is a bit medium purity, another one is very high purity, and all these centralized header, they can have different water purity and different water tariff. So what happens is industries, let's say they do not need fresh water, they can consider to buy from the several water headers that they have. And when they buy this water, they can buy it at a cheaper rate compared to buying clean water tap. And what's the benefit of having a middleman to manage your centralized water reuse system? The benefit is, like I mentioned just now, you can protect the confidentiality of the industries. Second, they are the ones that invest in the piping, the pumping, maintaining the pipelines, making sure that everything is okay, the water quality standard is being observed, any fouling or anything they will handle. So when you have someone that manage the system for the industries instead of the industries working it out themselves, so it becomes a business model. And they can also, and they also have the expertise, meaning they already know how to properly exchange water, recycle water. If you have these kinds of contaminants, how do you handle it? What kind of water which is acceptable, and so on. They are the one that do the quality assurance, make sure that the service is provided to the industries. And if there is any fluctuation, suddenly this plant shut down. Before this, maybe this industry supply water reuse, and then suddenly this one shut down. So what could be the backup plan that they have? So by having a middleman concept, we can make sure that there is a sustainable business model for a water reuse exchange across industries. And I'll give you another example. So let's say this is a conventional industry, industry 1. Before this, maybe they are buying water from water utility. So this is for Malaysia. So SAJ is a water utility provider from Malaysia, selling water at 3 ringgit 30 cents per meter cube. So before this company is buying this clean fresh water, 100,000 meter cube per year, and their water bill is 330,000 per year. And before and they are also producing wastewater, which 100,000. And let's say now, this wastewater, they don't treat it and they don't throw it to they don't send everything to the wastewater treatment plant. So maybe they segregate their wastewater. So the wastewater that they segregate, some are cleaner. So the cleaner wastewater that they segregate, they will sell it to the centralized water header. So the centralized water header, let's say they can buy the wastewater from the industries at this price. So it means that this company now can generate some income from selling their wastewater by this amount. At the same time, this company also, before this, they buy all the clean water from the utility provider. Now they only maybe need to buy 80,000 of meter cube of water. And the other 20,000, they can buy the second quality water reuse header. So this water will be cheaper. So the price may be selling at this price. So what happens is they will have a reduction in their water bill. And at the same time, they can also generate income from selling their wastewater. And the middleman that is managing it, they can also take some profit from this buying and selling of water. So this is the concept of centralized water reuse managed by some middlemen. And we can also talk about many things, like maybe we can think of feed-in tariff, like for renewable energy, but we can think of like, what if we use it for water instead? So maybe we have a feed-in tariff for water instead of a feed-in tariff for energy in the future, in order for us to promote water reuse across industries. So we have done some research in this area. There are a lot of models on how you can exchange water across plant. So among it is maybe you can use a one-way header. So one-way header is, for example, let's say I have a very long stretch of road. So I have one long pipeline. So the pipeline will pump water from plant A to plant B to plant C, plant D, and plant E. So I only have a one-way direction of pumping. So maybe because the industries is located. So I don't want to pump it two-way because it will mean that I have more water. So there is one concept that we have done where we consider only one-way direction. We also consider two-way. What if we pump two-way? Will it give more water savings? Or maybe because of the capital cost is too big, it's not practical. And there are also other models being introduced by other researchers, like by Chiu, 2009. So they propose some centralized utility hub. So let's say there are three different industries. So all of them pump the water to this centralized utility hub using different pipelines. And then after that, when they want to buy water, so they can buy back from the centralized utility hub. Another model is they maximize first the water reuse within their plant. And then when they have some remaining water, which they do not use, so then they send it to the centralized water mains. And there are still other researchers doing for batch process, adding some regeneration units, and there are just so many centralized water systems that you can look into if you're interested on. Yeah? Okay, so the challenges is like in Malaysia, the water tariff is still very cheap. And when water tariff is very cheap, it's very hard to drive water minimization projects like water reuse because the capital cost, maybe the payback period is 30 years and so on. And these are among the challenges. Even though we know water scarcity is real, but if water tariff remains low, that will be a challenge for people to invest in this kind of system. Second is if you want to go for water reuse, how do you ensure water quality and the continuous supply, reliability? And another important thing that you have to consider is when you are dealing with contaminants, the safety and the operability of the system. And next one is, let's say I want to propose the centralized system to Malaysia government. How do we convince the government or the stakeholders on the business model or the benefits of the system? So all these are challenges. And as the previous plenary have also mentioned, we should not only be looking at the technical side, we should also think of stakeholders, social acceptance, public acceptance, and so on when we are doing our technologies. Okay, so I've talked about this. So these are possible research directions if you're interested. We can look into more detailed system engineering modeling and of pipe planning, risk assessment, economics. We can do a lot of regulation planning, maybe see how we can work with the government. What kind of subsidy maybe the government can propose, maybe within 10 years, give a special tariff for water reuse. And then after that, they can maybe eliminate the tariff step by step, just like the feed-in tariff. What could be the social acceptance? Do the industries want it? How ready is our industries? What kind of training do we still need to give to the industries or the users? What kind of standards? Yeah, if you want to reuse water, what should be the standards? And people now are talking about smart energy system. We should also talk about smart water system. So if we can look into how we can connect IoT, big data analysis, and so on, also into the water analysis system, that will be superb. Yeah? Capacity building is also very important. How do we train people or give exposure to people about the importance of reducing water, going into this kind of technologies, and also some awareness programs and so on. So we need to have a merge, not only research by technical people, we need economists to come in, we need social people to come in, social study to come in, we need IT people also to come into the picture. So not only people from system engineering to do research. Yeah? So the key take-home message is water shortage is one of the world's biggest risks. And we need to engineer water sustainability. If we can train people or change people, that will be better. But if not, we have to engineer the water system. And when we engineer the water system, we should not look at one angle only, like reuse only. We should also look into elimination, reduction, regeneration, outsourcing, and other technologies possible to reduce the water demands. And finally, water minimization. If we can minimize it within our own facility first, that will be the first priority that we should do. But if it's not possible, because you don't have the expertise and so on, maybe we can also think how we can, someone maybe, for example, can propose like interplant water exchange with business model, like I showed with the middleman just now, and we can have a win-win business model situations. So that's all from me. Thank you very much to SDEWES especially for inviting me, and also to the grant funders for all our projects, and also to SPIL. Yeah? Thank you very much.
Thank you very much. I believe that everybody enjoyed it as I do. And we've got a couple of minutes for questions. Mohammed, please.
Okay, thank you very much for a very interesting presentation and the way you present it. Okay, I have something like a comment. Okay, he says shorter, please. Okay, if we see the supplier and the user of the water, for example, in I was working in water and sewage company. In my country, about 90% of the water is using for agriculture and this sort of things, and about 10% of the water is using for household and also industry. But when we see in the advertisement for the water to not use, the target is more for household and very less also for industry. For example, in the case of toilet and etc. But we need to do more research and pay attention more to the big portion rather than the smaller portion. So I would like to know about your idea about this comment. Thank you very much.
Thank you very much. So I do agree that agriculture is very important. It consumes a lot of water as well. My research is not in agricultural sector, but I do agree that we should try to find ways as well. Maybe change the DNA of the plant so that it consumes less water for the growing. So there are a lot of things as well we need to consider for agriculture, because let's say in Malaysia, we eat lots of rice. And rice plantation, you need a lot of water. So if we can find a special breed of rice, for example, that consume less water, so that means that we will need less water. But this will be the research for the maybe farming and agricultural sector. So what we have here is for the industries, but I do agree that agriculture minimization, water minimization, is also very important. Thank you.
Okay, thank you. Another one? Ja? Yeah. Sorry, I am making the order.
Thank you.
Yeah. Next time you will be the chair.
Okay. Thank you, Prof. Sharifah, for a very good presentation. I have one question. Is that you mentioned about the eco-industrial park. I would like to know, do you think if it's better that we do not reuse the water directly between the industries, but to build another centralized treatment station, because because the industries might be very different. If you directly reuse between the industries, it might be very difficult. So if there is a centralized treatment station, it can somehow unify the quality, the properties of this water, so it can redistribute to other industries. I would like to know what do you think about this.
Thank you very much.
Yeah, thank you.
All right, so I do agree that it's good also to centralize the wastewater treatment plant. But the problem is when you go into wastewater treatment centralized, it means you are cleaning everything maybe to the freshwater quality or the clean water tap quality. So that will mean you may need a lot of chemicals, a lot of energy. So it's good, but it also means you need a lot more investment. If we talk about water reuse means that we want to minimize putting treatment. If we put treatment, maybe it's only to reduce certain contaminants. Let's say bacteria. Bacteria is important, so maybe we put some chlorine inside the water, so you eliminate the problem of bacteria inside the water. It's just like swimming pool. Inside the swimming pool, so many people swim inside there, so many people do many things, but you still swim in a swimming pool, right? So what happened is We can use water reuse directly for many processes, even without treatment. So it depends on what kind of usage that you use the water for. I'll give you an example like scrubbing, gas scrubbing for toxics. You don't need clean water to scrap the toxic gas. You can also use secondary water. So what we are talking now here is it possible for us to take some of the water reuse from the companies, and then without maybe just some minor treatment or partial treatment, we try to reuse it for some process that do not require these clean water levels. In that way, you reduce your energy consumptions and so on.
Okay, thank you. Now the gentleman in the middle.
Thank you very much. Andrej Vojacek, Czech Republic. My point is we very often behave as the scarce resources in a society are unlimited. I wish there is more cost analysis in what we do. I give you a short example from Czech Republic. Nowadays we got a support scheme. It's called Dešťovka. It's about catching rainwater and using it for gardening and etc. I calculated the cost for 1 cubic meter catch, and it's nearly 20 euro per 1 cubic meter. While if you take a water from public pipelines, it's only nearly 2 euros, the average price in Czech Republic. So where is the sense? Where is the logic?
Okay, thank you.
Yeah, that's the reason that I mentioned just now. The water tariff is too cheap. So when the water tariff is too cheap, we don't look into options like rainwater harvesting, water reuse. But actually water is depleting. But maybe because of politics, for example, the government do not want to increase the water tariff, because normally, like in Malaysia, the water tariff is cheaper than the cost of treating the water actually. So actually the government is heavily subsidizing our water treatment. So if the government remove this subsidy, the water price is actually more expensive. So if water is more expensive, maybe rainwater harvesting will be more cheaper, for example. So maybe now the system that like outsourcing and so on is not practical because water is still cheap. But when the water scarcity happens in the future, when water is very, very scarce, water tariff will go up, and at that time it means you have to go into all these water minimization options. Yeah.
Okay, thank you.
Thank you.
One more. Yes, please.
Thank you for this presentation. Very interesting. I have a question regarding the situation in France, my country, in which I'm working since for 15 years on rainwater harvesting. And the question is, what about health issues? And more precisely, the question that it's very difficult in our country to make the rule change, regulation rules, because all the law, all the regulation process was made based on drinking water. So the idea is that with drinking water you can do everything, and each time you want to propose a project, they say, but it's safer with drinking water, so you can't do that. And there is no, you say that expertise is very important, and I do agree, but who is legitimate to make this expertise? In France, health society says, we are, and so you can do nothing.
Okay, thank you for the questions. So health issues is really a problem. So for example, let's say I take kitchen wastewater. So kitchen wastewater is, you have a lot of fecal contaminants inside there. So normally when we want to reuse water, we classify it into black water or gray water or brown water. So normally black water, we don't want to reuse it because it has high fecal contents and so on. Gray water means the water can still be reused for certain usage, but you have to be careful. For example, maybe you have to color the pipeline. So the pipeline cannot be the same color as the normal water, clean water tap. You have to have different color for the pipeline, and you also have to put labels. This is water reuse, do not drink, for example. And you need to give proper awareness training and guideline. So you cannot just implement water reuse just like that. you have to give awareness training, you have to have proper guidelines, you have to have texts and so on for the pipelines. And for example, maybe the water system, it has to be underground so that it doesn't mix with your other water sources. So there are actually ways to do it to handle the health issues that you mentioned. I'm not sure the regulation in France, but I have read that some countries, they do have grey water reuse guidelines. And maybe this is something we can adopt for other countries as well. Thank you.
Thank you. Anybody else? If not, it's perfect time for the lunch. Thank you very much again.